much more than I could talk about on the slide, so you could have it for future reference. But in reality, I'll probably only be able to pick up a few things on each slide until we get over to the details where I'd like to spend a little more time. So having said that, we better get started. Based on the learning objectives, here's what we will try to discuss today. To save time, I'm assuming everyone knows the dangers of tornadoes. So I don't have a lot of facts and figures on past ones for you. But I would like to ask, has anyone here personally experienced a tornado? A few? Yeah, I haven't either, although I've been watching tons of YouTube tornado videos over the last few years. And it kind of looks like my granddaughter Jessie did too, judging by the way she captured this funnel cloud in her artwork, which I thought was pretty grand. By the way, I want to say at the outset that the building code has provisions for both hurricane and tornado shelters. But today, if I only say storm shelter or shelter, just know that I'm talking about tornado shelter, since we don't get too many hurricanes around here. As far as acknowledgments, many of these names you'll recognize. They've been presenters here or sponsors here. I wish I had time to go through and tell you what awesome contributions each one made to the process over the last 5 years, but sadly we'll probably just have, only thing I can do is just say a big thanks and move on, but I really appreciate all their work. Here's some task force goals that we went through. Sorry for the typo. I meant to say just residential and not non-residential. You'll have to change that in your copy, I think, because I caught it after I sent it to Allison. Of course, the main goal was to study reinforced CMU shelters, which means we focus primarily on the structural related aspects. So if you're an architect here today, don't worry, I'm not going to throw a lot of formulas at you, but I did want to mention there's a great previous done study on a prototype classroom wing that goes through all the architecturally related aspects of a tornado shelter as well as the structural. But we didn't want to replicate that. We wanted to really drill down on how the CMU walls responded, and especially with respect to the connections that hold the roofs to the walls. You can get this prototype from the NCMA Foundation website, or I imagine that Allison could also get it to you if you're interested. On this slide, you can see the big lesson learned, and I'd have to say, in retrospect, the walls were easier to get to work than I expected, while the connections were harder to get to work than I had expected. But having said that, I would like to add that the roof-to-wall connections are so important to the stability and the success of any tornado shelter. We also focused on Group E construction, in other words, educational buildings, because this is one of the two groups that the IBC requires or mandates ICC 500 storm shelters for. The other group is what we used to call essential facilities, like 911 call centers, police stations, etc. But we decided to focus on educational buildings that are educational projects that would have storm shelters, which we're starting to see a lot of. Let's see. Okay, make sure I get everything down there. So let me make sure I didn't go too far. Sorry, did they mention I'm retired? It's been a while since I did some of the stuff. I actually brought 2 pairs of glasses because I wasn't sure which ones I would need. Okay, in terms of expected outcomes, it was this, no, wait a minute, sorry. Here we go. The first expected outcome was to hold a storm shelter summit, which we did here in this room in 2021 to figure out what we wanted to do and how we wanted to go about it. Again, many of the faces you'll recognize as past presenters and being around the Institute here. I called the attendees storm shelter troopers, and our slogan was, "May the force never reach you." So there was a lot of thinking, but we had a little fun too. And of course we had to go out for some Italian on the hill. That was a requirement. So it was decided to do 3 prototype studies and offer them up as shelter examples for educational purposes. And to that end, you'll see this red disclaimer here and also in the drawings and the report. And the key thing I just want to mention there is that we're not intending these to be shovel-ready documents. These are just examples, or it's a snapshot really, of a particular building responding to a tornado. But hopefully they'll be useful as examples in the future. As far as some of the decisions we made, and most decisions were related to challenges that came up, things we hadn't thought about before or whatever. And again, I'm sorry, there's a typo here, but we did select CMU for the walls. I guess there's no surprise there. However, I will say that structural clay units could also have been used. You can design them practically the same way you can concrete masonry units. So that is an option. We decided to go with 1 small classroom and 2 sizes of gymnasiums, and all 3 would have varying roof systems. We knew going in that the walls were going to need to be fully grouted, and that's primarily to provide the MISL impact resistance that the ICC and FEMA, for that matter, require. And so we just automatically assumed we were going to fully grout these walls, although I think we probably would have got there by design anyway, due to the high wind loads. Speaking of codes, in 2021, when we started the project, we decided to go with the 2018 IBC because most of the country was using it, or an older version. That, of course, has just shifted some since then, as areas have moved on to the 2021, as you can see there in the green box. However, since the 2021 IBC still references the 2016 editions of ASCE 7 for load determination and TMS 402 for masonry design, we decided to go ahead and complete the project as we went along under the 2018. And we don't suspect there would be a lot of structural tweaking that would have to take place if you wanted to look at these examples in terms of the 2021 IBC. 2024 would be a little bit different, but now FEMA P361 is another standard you could use for shelter design for safe rooms, or as FEMA calls them, safe rooms. In general, if the shelter is designed per P361, it will also comply with ICC 500. And though we didn't use it directly for the prototypes, we did incorporate some P361 items into the design where we thought it was prudent. And one example of this is we decided to go with their guideline of increasing the internal pressure related to the external wind from 0.18 to 0.15, which is about a factor of 3. So we thought, to be on the conservative side, we would go ahead and do that. On a normal building, you could probably count on 0.18, but in the with a storm shelter, we decided to go with a 0.55. A quick note about ASCE 722. They have added Chapter 32 on tornado load. And it's a new chapter, but it doesn't apply to ICC 500 storm shelters. So if you're required to do a storm shelter under ICC 500, then in the future this chapter would not apply to you. What I believe the goal here is they're trying to bring more storm resilience to the structures that are on the edges of the storm path. And so they're looking at EF0, EF through EF2, trying to increase the amount of wind those buildings are designed for in the future. But as I said, if you're using ICC 500 to design your shelter, this chapter will not apply. And it won't apply until people start adopting the 2024 IBC. Back to some decisions made. Locating the prototypes right here at the Masonry Institute seemed to make sense, since this building is located at the heart of the 250-mile-an-hour tornado zone. As for seismic, since we were going to use joint reinforcement for crack control already, And since we expected wind loads to govern over seismic, which they did, we went with seismic design category C to limit the minimum seismic horizontal reinforcement required to W1.7 joint reinforcement, 16 inches on center vertically. Now, if you compare that to seismic design category D, that minimum would likely jump up to a number 4-bar minimum at 4 foot on center vertically. But since the wind loads were going to govern, we didn't want the prototypes to imply that you had to have horizontal reinforcement just because it's a tornado shelter. If your project is closer to a fault line and your ground motions get worse, then the seismic could come into play. And we tried to do a discussion of that in the Appendix B of the report, where we took our prototypes and set them in Cape Girardeau and looked at what that did to the wind and seismic loads. Prototype loads, we used 100 PSF live load. That is required by ICC 500. And since we're not doing a complete roof system designs for these buildings, we had to make some assumptions on dead load. You can see those assumptions there. In terms of rain load, it's kind of an interesting one. You know, all buildings, unless they have positive drainage, need to be designed for rain loaded ponding. But there's a lot of variability to that. We didn't know the final design of the roof and the slopes and where the drains were going to be. So since you don't have to check live load of the roof live load and the rain loads at the same time, we just decided to put a note on saying, hey, your rain loads need to be less than 100 PSF for these buildings. Let's see. Here you can see some additional parameters that are used for the wind and seismic load. The shear wall system that we selected was an intermediate reinforced masonry shear wall, and that again allowed for the joint reinforcement to be used as the minimum seismic horizontal reinforcement. And at the very bottom, I've got a quick comparison there of the out of plane wind load on walls. This is for the third prototype, the bigger prototype, the high school gym. And just a quick comparison of that out of plane load. And you see seismic is 30.7 PSF and the wind is 210.2. So quite a bit of difference in the loading there. Another comparison I put together for this presentation is non-shelter versus shelter loads for the building given at the top right corner. The top line is for non-shelter. The second line is if the same building is a shelter. And the bottom line represents the shelter loads divided by the non-shelter loads. And you can see, again, quite a bit of an increase there across the board. So we're dealing with pretty big magnitudes. Here are some decisions related to the CMU walls. We decided to go with a unit density of 105 PCF or pounds per cubic foot. We chose that because it has pretty good availability and also because it would be on the conservative side in terms of calculating wind uplift, right? Because the lighter the walls are, the more uplift is going to try to get its way down to the foundation. F'(M) that we went with is greater than the current default of 2000 PSI, but we considered that the higher values could still be achievable in most regions, given the block strengths that are being used. Mortar and grout is pretty much your standard call out, nothing much different there. On the steel side, we went with ASTM A16 grade 60. Some of those bars need to be weldable, and you can see the joint reinforcement that we've already talked about. Now, anchors, the bottom bullet there, we didn't wind up using any anchor bolts or post-installed anchors. You could. There's no reason we couldn't use them on a storm shelter. But just the way the connections, the way we analyzed the connections, the path we went down, we decided to take a little bit different approach, which you'll see a little bit later. On the design method, allowable stress design can be used for shelter wall analysis, but for a few technical reasons and preferences, we decided to go with strength design. And also, since most design calculations fell to me, which is probably why it took 5 years, and since I'm not a finite element or 3D model jockey, all the analysis was done either by hand or by spreadsheets that I had developed over the years here at the Masonry Institute or while teaching structural masonry at Missouri S&T. Again, since we're not doing complete and final designs for the prototypes, we did employ the by others notation in some key areas. This applied mainly to the foundations and the roof systems. We did assume that the masonry walls were pinned at the top of the foundation wall and at the roof system. And we also gave guidance with regards to what the walls needed in terms of doweling into the foundations. But otherwise, everything else with the foundations you'll see is pretty much just by others. We did the same thing on the roof, but we tried to be a little more descriptive there by including a special note on all the prototypes, indicating that final coordination between the designer of record and the roof system manufacturer or supplier is certainly required to come up with final designs for these projects. We made the best assumptions we could. We tried to follow the industry literature as best we could, but there's just some things we didn't know about as we put things together or couldn't know about. Now, tornado shelters in almost all cases will experience net uplift coming from the roof system as delivered to the walls. And what I'm calling a tie down here is a dedicated vertical bar in the wall solely to connect that uplift directly down to the foundation. In that case, all the other vertical bars in the wall are just there to handle the out of plane load hitting the face of the wall, which puts that bar in tension. However, for the prototypes, we were able to size the walls and the vertical reinforcement to do double duty, which means the vertical bars within the wall can handle both the out of plane wind load and deliver the net uplifts simultaneously and safely down to the foundation. So you won't see any tie downs, what we're calling tie downs in the prototypes, but that is certainly an approach you could take on some of these high uplifts. As far as the bottom of the wall, whether or not you'll have net uplift there is pretty much dependent upon how heavy your wall is. Because if you have net uplift at the top, you start subtracting that net uplift by the weight of the wall as you go down. If you overcome that weight of the wall, then you will have some uplift there, which has to be accounted for. Another thing that we decided to do was all roof and floor diaphragms, your horizontal floors and your roofs, they kind of hold everything together, need to have cords to help them act as beams so they can deliver its load to the walls. On a normal CMU building, this is typically done in the top course bond beam, as you can see on the left there. But for our shelters, where the loads are quite a bit heavier, especially on the uplift, we decided to take the other option, which can be done, and that is to show the diaphragm cords within the diaphragm itself, as you'll see in the, maybe I should get the laser going, if I can find it. There. As you can see right here, this is the diaphragm slab, and we're assuming that the diaphragm will be placed there. That just kind of lightens the load in what we're expecting those bond beams to do at the top of the wall. And as you can see, you also get a certain amount of distance between, if you do the diaphragm here, which often works, there's quite a bit of difference between the diaphragm forces here that all has to be gotten down to the bond beams. We still have to do that here, and we did, but this at least kind of lightened its work that it has to do. And by the way, these circle arrows, those represent the kind of top of wall moments that get induced as the floor does what it does, or the roof, okay? And as you can imagine, if you have a storm shelter with a lot of uplift coming from the roof, that wall is going to have a lot of rotation on it. And so we wanted to make sure that our top of wall connection and the bond beams there were able to handle all that. Now, many, if not all, low-rise school buildings have wall extensions or we call parapets. But again, we wanted to focus on the walls themselves, so we decided to go only with enough top-of-wall extensions to provide coverage to the roofing, what we anticipated to be the roofing, and in some cases to provide the missile impact protection required. What we did then do, when we calculated the winds, we took the overall height, you can see the 16'8" there in this case, as the height of the building when we did all of our wind calculations for the main wind force resisting system and the components and cladding. Now, you can have parapets on a storm shelter, but you kind of have to make a decision as to whether you want them to remain during the tornado or are you considering them to be sacrificial, okay? If they're not sacrificial, then you have to design them to withstand the same tornado wind loads as the rest of the wall. And you have to figure out what impacts that has on the rest of the wall, plus your connections and everything else. So you can certainly have parapets, but you just have to make another decision and maybe some extra design there. We kind of wanted to simplify that because if we show a 2-foot parapet, then somebody would want a 4-foot parapet. And if somebody, anyway. We didn't include any anchored veneer on the prototypes as well, although we do expect that many CMU storm shelters would have at least some areas of anchored veneer. But similar to the parapets, if you're going to have anchored veneer, you again have to decide, are you expecting the anchored veneer to stay on during the tornado, or is it sacrificial? And if it's not sacrificial, then you have to engineer the anchored veneer system again to withstand those tornado loads. And just a note that those tornado loads will always exceed the loading that's designed to in TMS 402 Chapter 13, the anchored veneer chapter. They're good for normal building wind loads, but not for the storm shelters. The masonry module was used religiously throughout the prototype, which is always a good recommendation. We use standard CMHA empirical vertical control joint placement, which is a 3/8 inch wide joint, spaced no more than 1.5 times the wall height, or 25'4" maximum, which if you look into the drawings, you'll see we did hit the maximum a couple times because these walls are tall. In terms of the control joints, we do expect the horizontal reinforcement, the joint reinforcement primarily, to terminate at control joints. But at the top of the wall bond beams where the connections are going on, we expect the grout and the horizontal bars in those bond beams to go through the control joints for continuity, for the sake of the building. We use traditional hand calc approach for masonry openings. You can see an illustration of that here at the left. On the ends there, where these green arrows are here on each end, these are what we would call your normal wall panels, which they take lateral load and vertical load. They take the vertical load down to the foundation, and they deliver the lateral loads both to the foundation and the roof. At the opening, we assume that the masonry over the opening delivers its load down to a masonry beam. The masonry beam then delivers its load laterally to these gray areas, which we call jam wall panels or jam panels. The doors are also assumed to be strong enough to deliver their loads laterally to the jam panels. And then the job for the jam panel is take that extra load, in addition to the load it would have gotten anyway, and deliver those up to the roof and the foundation, and also deliver any vertical loads down to the foundation. Now you'll notice here that the opening is centered within a control joint spacing. That was done on purpose to maximize the amount of masonry you would have on each side of the opening. And you'll see that's typical for all the prototypes. On the right, we have a little example of the transition in the vertical bars in the wall as you go from the standard panel to a jam panel. So typically, to overcome that extra load, we have to beef up the jam panel. And one way to do that is to go from 1 bar per cell to 2 bars per cell. And then you'll notice that you need to watch the bar cover on that offset bar, which we're showing here is 2 inches, which was typical for what we held for the prototypes. The standard TMS 402 lap splice from chapter 6 was used. The results of that is tabulated for each prototype within their drawing sheet. Now, some links were rounded up, and some cases we recommend going to mechanical couplers. As you can see, this is a threaded mechanical coupler here, where you could avoid doing the lap length, because some of those with bigger bars gets pretty long. But you can do it if you think you can build it. But we also said, hey, you might want to consider an alternate there. Okay, so that brings us to the task force deliverables. Sorry, that was kind of quick, but I wanted to get to this section so we'd have time to kind of go through the drawings a little bit. As I said, I have more information that I knew I could cover, but I wanted you to have it for future reference. And so now we can take a look at what the prototypes actually look like, which is really the main deliverable, I think. Here you can see 3 sets of drawings, one for each prototype, and then the report on the right. You have the drawings in front of you, so hopefully that's helpful as we go through. You don't have the report unless you've already downloaded it, if you're good at doing those kind of things, from the QR code, but you can certainly download it later. And I think we're going to be giving away a couple bound copies of it at the end there, which I'm sure someday will be priceless. Okay, here's a short summary of the prototypes, given the footprint size, wall heights, CMU size, and the roof system used. If you're wondering about ceiling heights, I'm not addressing that here, but for the music room, the smaller one, we assumed they would probably put a drop ceiling anywhere they wanted to below the hollow core panel roof. For the elementary masonry school, the clear height is set by the bearing height for the double T's, which is 26 feet. And for the gym, high school gym, the clear height is going to be around 30 feet. We're using a top chord long span truss there, so it really kind of depends on how far down that joist winds up coming, but we're estimating about 30 foot of clear height, which should be good for most volleyball, basketball, and things like that. Just a note about the high school gym walls, you can see it's 16 inches. We could get them to work at 12-inch CMU, but for the sake of the top of wall connections and a few other things that came up, we decided to go with 16-inch units for that larger gymnasium. Now, while 16-inch units are not real common, the modes are available, and they have been produced in the past, and I think I saw Mark's here with Midwest Block, so if you have any questions about that, I'm sure he can help you out. Of course, the recommendation would be to do that prior to the project, is get with your manufacturers and make sure those are available. Okay, first the elementary music room, and if you had some interior partitions, this may be a small classroom wing. You can see the simplified floor plan at the left, which is a clear span. The hollow core plank roof system spans from the top to the bottom of the plan, which determines which walls are load bearing and which walls are non-load bearing. It has a double door on one end and a single door on the other, and there are two windows on each of the other 2 walls. Now, can you have more openings than this? Absolutely, but you just have to remember every opening weakens the stability and the strength of the structure. So that has to be accounted for and overcome, and you really have to keep in mind with the kind of wind loads that we're dealing with here. So for our prototypes, you can see there by the elevations, what we're doing at the openings, where we have the openings centered within control joint spacings with designated jam panels. We also decided for the reinforcement over the windows and below the windows, these are beams, CMU beams. Whatever reinforcement they required, we extended those to the outside edge of the jam panel, the designated jam panel. So This prototype is 8-inch CMU with an F'(M) of 2500. The next one is the elementary middle school gym, or perhaps could be just a general activities room. Again, the simplified floor plan on the left, which shows the roof spanning, in this case, which is a double T system, from top to bottom of the floor plan. That again determines which walls are load bearing and non-load bearing. We have double doors on each end that are offset, and then we have 2 windows on each of the other 2 walls. And again, the way we handle the openings are the same as the previous prototype. This one is 12-inch CMU, again with an F'(M) of 2500. The third one, and the largest one and tallest one, is basically a square clear span space. And we consider this might be useful as a high school gymnasium. You can see you have some option for some bleachers there. There are double doors on each end, which are aligned with each other. And as before, we have the 2 windows on each of the other 2 walls. And again, the openings are centered within control joints, and they're handled the same way. Now, these are the walls that are 16 inches, and because of the extra load coming from the larger building, we went with F'(M) of 3000. Now, here's a summary of the calculated wind loads for each prototype. As you can see, the loads generally get larger as you go down and to the right. This is as the shelters get larger, bigger, and taller. The top of wall uplifts are shown as uniform loads, but this actually only applies to the music room, where the roof to wall connections were actually at 24 inches on center. The gymnasiums have roof members spaced at 4 foot and 4'8" respectively. So their uplifts actually get delivered as concentrated loads. We're at their setting points. And so we had to account for that, converting that uniform load into concentrated loads. The top of wall and bottom of wall uplifts shown are for load bearing and non-load bearing non-jam. So this doesn't show the load that the jams are getting. Just wanted to give you an idea of what was going on with the regular loads. Note that the load-bearing bottom of walls have uplift. Not a whole lot, but they do have some uplift, while the non-load-bearing do not, because the load is usually lighter on the non-load-bearing side because the roof member is parallel to that wall, so not as much load is coming to that wall, and doesn't overcome the weight of the wall. Here's a summary of the vertical bar reinforcement for each prototype. Now we're including non-jam and jam panels. This reinforcement is also shown in each set on what we called the reinforcement elevations. Generally, they're on sheet 6 and 7. Note, since we were trying to max out the wall heights, almost everything is 8 inches on center, and in most cases, 2 bars per cell. At the right end of the table, I also have what the vertical reinforcement might look like if the same prototypes were designed as non-shelters, just for comparison. Of course, a couple of the biggies there is the unit sizes on the gymnasiums went up or go down if it's not a shelter, and then of course the reinforcement is a lot less. Okay, let's turn now to some top of wall and bottom of wall connection details. First, the elementary room. This is for load-bearing non-jam and jam wall panels. So looking at the detail at the left, we assume that the mason will build up the wall to the 14'8" mark. Excuse me. Top that with 2 courses of reinforced bond beams. The bent bar connector here would be left extended until the hollow core planks and the concrete topping slab is ready to be put in place. Then that bar can be bent down, and then the diaphragm concrete topping slab can be placed, and then the mason can finish out the little extension here to complete the wall. Notice here, I don't know how you all do this, but this bent connection bar is actually in line with the vertical bar, which is indicated by this distance or dimension of 0 space there. So you have to imagine that's in line, but we offset it so we could see it. The length of the bent connection bar in each direction is based on the development length we're expecting to be needed into the top chord slab or the diaphragm slab. And the detail on the right is basically the same thing, except this is for when you have lamb or when it is a jam panel condition. So it has 2 bars per cell because it's getting extra load, but most everything else would work the same. If we look at the non-load bearing condition, both for non-jam and jam, you can see now the hollow cores are turned the other way. Most everything else is the same. We decided to go with the same bent connection bar in both cases for consistency. And yeah. So looking now at the bottom of the wall details for this same prototype, we have the non-jam conditions shown. Sorry again for the typo. I was getting my titles crossed up. So this is for these are non-jams, but it's load bearing and non-load bearing. Anyway, the left detail is for the non-jam load bearing wall, where the dowel is married to each vertical bar due to the uplift coming from the wall and to offset the out of plane and in plane wall shears that are felt between the bottom of the wall and the foundation. The detail on the right is for the non-jam, which receives no uplift and only resists the wall shears. Accordingly, it's not quite as heavily reinforced. You can see there's a dowel at each end of the wall panel, which we assume is where the control joints are, and then 16 inches on center in between, which is basically every other vertical bar, wall vertical bar. This is for the bottom of the wall jam panel conditions, both load bearing and non-load bearing. Once again, sorry for the typo. The left detail is for the load bearing jams, where the dowels are again married to each vertical bar due to the uplift and wall shears. So we have 2 bars per cell. Each bar is to get a dowel bar into the foundation. The right detail is non, so it has less load, and again, those dowels are at the end of each wall and 16 inches in between, basically every other double bar location. Moving on now to the middle school gymnasium. Here we have the 12-inch wall will be built up to 26 feet, which serves as a bearing point for the ends of the double T. The double T is welded to a slotted plate. It's not really called out here. We'll see that here in a minute. Is welded to a slotted plate, which is then welded and bolted to the masonry plate below. The masonry bearing plate is connected down into the 12-inch wall with 4 reinforcing bars, 2 of which are welded to the plate and 2 of which are threaded bars passing through the plate. The 2 outside bars transfer the lateral load from the top of the wall, 12-inch wall, into the double T system. The inner 2 bars are there to transfer the uplift coming from the double T into the wall below, and also to reinforce the wall below to overcome any moments that double T is going to put into the wall. Above the 26-foot bearing height, we have a 6-inch CMU closure wall to enclose the ends of the double T's and provide MISL impact protection. The closure wall in this case also delivers the in-plane shear from the concrete topping slab diaphragm via some similar bent connection bars at the top and vertical bars extended down into the 12-inch below. It delivers that shear from the diaphragm down to the 12-inch wall below. So that 6-inch wall is actually acting like a short cantilevered shear wall to do that action for us. We anticipate the closure wall will be built after the double T's are set, because it's kind of hard to swing those in, and prior to the placement of the concrete topping slab, at which time the connector bars can be bent into the diaphragm. The rest of the 6-inch CMU extension at the top can be built after those are in place. So these details should help us further visualize the connection we were just looking at. I've also color-coded some of the items to hopefully make things a little easier to follow. On the left detail, you can see the masonry bearing plate colored green. Hope that comes through. And the two welded outside shear bars colored blue, along with the two threaded bars passing through the plate colored red. Above, you can now see the slotted plate called out as mentioned before. Now, maybe a little hard to see, but the slots are parallel to the length of the double T, okay? And that's to allow for some adjustments and movements while the double T dead load and the concrete topping slab dead load are being placed and they're all settling in. Once that settling in happens, then the nuts and the washers and the final welds, you can see that we have two welds. The first weld, which is to weld the double T to the slotted plate, and the second weld is to weld the slotted plate to the bearing plate after things have been set. And then the nuts and washers can also be final tightened to make that a final connection for the system. Now you can see this also in the right-hand plan view of all this. Again, we got green plate, masonry plate outlined in green, the blue shear bars, and the red tension bar moment bars. Now, to help visualize this is just a sketch idea while we were doing this. I was interested in how those concentrated loads coming from the double T's would find their way down on the wall. And we followed TMS guidelines on this, which is a 1 to 2 distribution. And you can see I used the same color coding here. You've got the green for the plate. The blue bars, which are the shear bars, they're 24 inches long. The red bars are the uplift bars and moment bars. They are 32 inches long. So you can see the red bar kind of extends itself down past the other bars. And you can see the influence areas here in the dotted lines. These lightly gray dotted lines represent where the horizontal reinforcement is in the top of all bond beams, and also the beams that are over the opening. This is the condition for the non-load bearing where the double T's are running parallel to the wall. This is actually a little simpler. We went with the same, the 12-inch wall can be built full height since we don't have to provide bearing for the double T's. And we use another bent bar connector to connect to the diaphragm of the double T's. You'll also notice for consistency, there's two bond beams at the 26-foot height for the bearing. We decided to run that all the way around the building, just so there would be no, confusion about where those bond beams start and stop. As far as the bottom of the wall, again, one more typo. I think this is the last one. The left detail is for load-bearing walls and load-bearing window jamb panels, where we have a dowel at every vertical bar due to the uplift and the shears. You can see the call out here that the length of those dowels up into the wall will be based on the lap splice table on sheet 211. If you go there, you'll see those lap lengths based on the bar size and the location. And you'll see some of those get long, so that's where we have this, why we have this alternate note here in case they want to use mechanical couplers. The right side is for the non-load bearing jamb walls and door jambs, and you just have the one dowel in the center at 8 inches on center. Moving on to the high school gym where we have the long span joist, which you can see the top chord bearing condition there. Though everything is bigger, going with the 16-inch walls and the way the top chord bearing allowed us to do things, detailing got a little bit easier actually. So we do have 16-inch walls that would be built up to the 36-foot point, which serves as the bearing point for the ends of the joists. The joists are welded to a masonry plate, which is connected to the wall below. Again, with 4 bars. In this case, they're all the same length, but they are doing the exact same things as the previous prototype. The length of these bars, because of the bar size and because of the cover distance we had available, went to 56 inches. Above the bearing height, we have a short 6-inch CMU closure wall that encloses the ends of the joist and the roofing and provide missile impact resistance as needed. The closure wall in this case was analyzed as a short cantilever resisting its own out-of-plane loads only. And those were wind loads, by the way, or tornado wind loads. Because we expect the shear will go directly from, this will be a composite roof, so the shear of the diaphragm will go directly through this joist end. And so we've got a note there for the joist manufacturer to be sure and look at that, make sure they have enough rollover resistance in these joist ends to get that load down to the wall below. The closure wall in this case is reinforced by just extending the outside bar of the wall below. And again, we anticipate the little closure wall to be built afterwards, after everything's in place. Here's a plan view of that same detail. You can see the green masonry plate. You can see the 4 bars used for shear resistance and uplift. Yeah, I think that's pretty good. This is a non-load bearing condition, where again, we're building the wall up to 38 feet since we don't need to provide bearing for the joist. And again, we're using that same bent bar connection, connecting the wall to the diaphragm topping slab there of the roof system. Here's a case where we looked at doing anchor bolts, but we just felt like to be consistent, we went with this bent bar situation. Bottom of the wall conditions, very similar. We have dowels that match the vertical bars when it's load bearing because of all the uplift. If you're non-load bearing, you get a dowel just required in the center. Now, both the gymnasiums had an interesting little detail at the top corners of the load-bearing walls. If you turn to sheet 2.3, this is for the elementary middle school gym. On sheet 2.3, you'll see 2 elevations there. And up in the upper right corner, you'll see a little bit of something going on up there. Well, what's going on is because the non-load-bearing walls come through, when you build up to the closure wall, and the end wall, those larger units are going to go through, and the 6-inch unit needs now to die into the end walls. And you can see that shown here in this plan view detail, where we have the 12-inch units coming through to the corner. But here we need to provide the bearing for the double T, so this is a 6-inch closure wall. And then where those come together, we decided to put a short control joint just to allow, if there's some movement over time between those two, they won't push on each other too bad. Now this detail here is just to show how mason contractors always do a 12-inch corner. If you're not familiar or not aware, a 12-inch corner doesn't turn all that nice. Well, I should say it's not as nice as an 8-inch unit. So they always have to do something at the corner to make that work out. We're just kind of replicating that here. Likewise on the larger gym, except now we have 16 units trying to transition to 6-inch units. And on the other one, we didn't have a control joint below nearby, but on this one we did. So we decided to run a short horizontal movement joint over to that joint, just again, so we could allow for some movements there. Down here now, 16-inch units do work a little nicer at the corners because they're on module. You can use full units and half units. Okay, well, that's a quick overview of the prototype drawings. I know it's really fast, but you've got them there in front of you. If you ever have any questions, you can reach out to Bruce or Greg, and they can get a hold of me if needed. But I want to start real quickly, wrap some things up on application. You know, we hope that you all can use these as examples. We hope that they show that concrete masonry units, structural concrete masonry, can be used as tornado shelters. The wall heights that we're showing, you can kind of consider as maximums, but of course, your own shelter that you may be trying to design may be shorter, whatever the case may be, and you may be able to do some things a little bit differently. Just remember that these are not shovel-ready designs. There is a lot more decisions that need to be made. One thing in particular is the code requires independent peer review for final designs of tornado shelters. So that's something that would definitely have to be done. One thing that I didn't touch on or have time to touch on is quality assurance, quality control. For shelters, special inspections and verifications are definitely in play. They're even more important. Also structural observations, which requires an engineer to look at the structural system anytime there's a high elevated wind load, so that would also need to be done. The other thing is cost and scheduling. We did try to address that in the report. If you go to Appendix C, I guess that was for cost. Is that right, Greg? You'll see a discussion about what we think these prototypes may cost if you tried to build them here. If you'd like more information on that, you can contact Greg. He can help you out with that, I'm sure, or give you some preliminary data on any storm shelter that you're looking at. Future research, I understand there's discussions going on now to have some universities look at the connections that we've proposed to see how they work under, university testing loads or university testing. Maybe that'll lead to new unit configurations that'll make things easier. I would like to see some finite element modeling done in the future on these prototypes, just to see as a good cross check on what we did by hand, especially how things happen or how things respond around the openings. And I think all of this research, potential research, is in line with what the CMU checkoff would be interested in. So I'm sure we'll be seeing some of that going forward. Well, that's all I've got for you. Thanks for listening fast as I rambled through this. Also want to thank today's sponsor, High Camp Masonry, a great mason contractor. Luke Siebert there is on the TMS code committee, which really helps us a lot getting their feedback. I'll be around after the seminar if you'd like to ask some extended questions. But as I said, you can reach out to Bruce anytime and Greg, and they can include me as needed. And with that, again, I'll say thanks again, and good to be back with you. Almost time for questions.
Yeah, does anyone have anything quickly? Yeah.
What is the requirement for
in terms of it being a storm shelter? No, you can use the standard as a, I keep wanting to say NCMA, the concrete masonry hardscapes recommendations on placing control joints, which is a